Good evening, everybody. Welcome to the sixth ThorCon training and workshop. Tonight is a very special night, and next week we still have the very last session, but there would be any presentation. There's only 2 hours of question and answer. So prepare your question and answer. And also the non-vision testbed platform, which hopefully by the end of next year will be start construction, and many things will be tested. That are the purpose of the non-vision testbed platform. So everybody, so without further ado, Kun, please, you have the floor.
Thank you very much, Bob.
Okay. Yes.
Yes. Thank you very much. Again, welcome all to this ThorCon workshop. It's amazing that it has been 6 weeks. We have seen a lot of participants over the 6 weeks. I mean, we have been enjoying the discussion with you guys. So let me share my screen here. My PowerPoint presentation. Okay. So let me put it into presentation mode. Can everyone see my screen?
Yes, yes.
Okay. Yes.
Okay. Thank you. Okay. So we're into the week number 6. Today we're going to talk about the ThorCon design and safety assessment process, and then we're going to present a few typical MSR events. So the first part of the presentation is about the overall design and safety philosophy, process, and thinking. And then the second half of the presentation is going to be about a typical MSR events that we analyzed, and we're going to present to you the conclusion we have got from those analysis. So this week is the last week of the presentations. Next week, we're going to have the a Q&A session, and hopefully we'll be able to answer most of your questions in week 7 next week. Okay, so let's get started. So let's start with the safety philosophy of ThorCon. I think it's important for us to have a review of the ThorCon safety philosophy, that we can understand why ThorCon is doing the things that we're currently doing. So I'm trying to summarize the safety philosophy of ThorCon in a few sentences here. ThorCon's safety is based on control, cool, and contain, and we call it 3 C's. Control, of course, is the control of reactivity. Cool is about removing the heat that is generated in the fuel, not only from fission, but also from decay. Contain is the confinement of the radioactive material, the radiation. These 3 C's are actually consistent with the fundamental safety functions that was identified by the IAEA in their safety standards. So how does ThorCon implement this control, cool, and contain? So we started with eliminating the hazards by design. So instead of start with mitigation methods, we start with eliminating the hazards. So there's mainly 2 sources of hazards. The first one is human errors. If you review the history, you will find that many of the past accidents were actually caused by, or partially caused by, human errors. So what we do is we, in the design, instead of having procedures, systems, and that can mitigate the human errors, we we eliminate the possibility that a human error could impact the safety. And of course, we cannot absolutely eliminate 100% of human errors, but we try our best to the extent that is possible to minimize the impact of human errors. The second source of errors is the loss of power. The second source of hazard is the loss of power, because a lot of systems are using power. So if you lose the power, sometimes the system won't be able to function as it designed. We eliminated hazards by using systems that are not depending on the power. So even if we lose the power, it's not going to stop the systems from doing its functions. So we're going to explore how we're going to do this in the future slides. But here are the two major factors that we considered in the design. But realistically, even if we try our best to eliminate hazards, there's still going to be hazards, right? There's still going to be internal hazards and external hazards. In order to manage the residual hazards, ThorCon is following the defense in depth concepts that is consistent with the IEA requirements. Again, in the future slides, we're going to discuss how ThorCon is doing defense in depth. And with elimination of the hazards and the defense in depth to manage the residual hazards, which will generate a design that is much safer than the previous generation of nuclear power plants. But how do we validate that? How do we verify that? We do that by test. So we intend to demonstrate the safety, demonstrate the requirements are met by tests, instead of relying on procedures, relying on analysis, we're demonstrate our safety by tests. So the test, as Bob just mentioned, the first step of the test is the pre-fission test. We're going to construct a full-scale test bed without nuclear fuel to demonstrate the safety. Then the plant itself will also be a test bed. We're going to do a test with nuclear fuel, and so that we can accumulate experience, that we can further improve safety for the future power plants. So to summarize, we start with the idea of control, cool, and contain. We eliminate the hazards, the human errors, loss of power. And then for the hazards that we cannot eliminate, we follow the defense in depth concept. And then all this will be demonstrated by test. So these are the summary of the ThorCon safety philosophy. Okay, so with this philosophy, how do we actually implement this philosophy to ensure safety? So we start with safety objectives, goals, and acceptance criteria. So let's review the hierarchy of the safety objectives. So we start with the general safety objective. So that includes everything. It's not only about radiation, it's also about worker safety, fire safety, everything you can think of. And within that general safety objective, we have radiation protection objective. So what the IEA is focusing on is the radiation protection objective. So IEA is focusing on the ionizing radiation hazards. So it's only part of the general safety. And then once we establish the radiation protection objective, we have to have some quantitative values so that we can conduct analysis to demonstrate the safety. So under the radiation protection objective, we also have the radiological acceptance criteria, which commonly it would be dose rates. And so in some cases, just having the dose rates are not enough. The radiological acceptance criteria will be complemented by safety goals. And those safety goals can be qualitative or it can be quantitative. So those are the radiological or radiation objective, but we have to convert it to a technical acceptance criteria. Because in the day-to-day operation, we operate a system which has temperature, pressure, leak rate, and those limits, those technical criteria are actually from the radiological acceptance criteria. So let's go into the next few slides to examine those objectives more closely. Okay, so let's start with the general safety objective. So what is ThorCon's general safety objective? And our objective is to protect individuals, society, and the environment from harm. Knowing that we're saying harm, which including any type of harm. On top of that, furthermore, we consider to and strive to reduce the overall risks to the society and to the local and global environment. So when we think about the safety, we're not only thinking about the risks that are introduced by the plant itself, but also the risk that could be reduced by introducing this plant to the society. So, for example, when we build the power plant, it will inevitably introduce some risk, but also by providing this power with almost no carbon emission, no pollution, it will also reduce the overall risk to the society by reducing the pollution, by reducing the carbon emission, by providing reliable electricity to the society. Overall, it will also reduce risk. So when we think about the risk, we think about the overall risk. So this is the general safety objective. And under that, we have the radiation protection objective. So our objective is to protect individuals and the environment from any harmful effects of ionizing radiation by strictly following the radiation dose limits prescribed in regulations. So there are two things I want to emphasize. The first one is harmful effects of ionizing radiation. So we're trying to protect individuals and environment from harmful effects of ionizing radiation. So not all ionizing radiations are harmful. So we're focusing on protect against those harmful ones. And second ones, we're doing that by following the radiation dose limits in the regulations, which give us a quantitative limits. Okay, so those are, as you can see, those objectives are really top level objectives. So we have to convert it to quantitative values so we can actually implement it in the design and demonstrate it through the safety assessment. So that introduces the radiological acceptance criteria. These are the quantitative values. So for the plant situations, which basically the normal operation, the dose limits will be under the limits prescribed in the Schedule 3 of IEA Safety Standard number GSR Part 3, which is actually the values that are the limits that are accepted by the international community. So we will be under those limits. On top of that, we also have a acceptance criteria that just for the accident conditions and also the LOs. So the committed whole body dose for any member of the public at or beyond the site boundary for a period of 30 days after event will be less than 0.5 millisV for any AOO and less than 20 MSV for any DBA. Again, these values are commonly used in the international community. So by defining this quantitative limits, we have an acceptance criteria that we can use in our safety assessment. So if our safety assessment demonstrates that the values are under those limits, we can consider it to be safe. However, on top of the acceptance criteria, we also have a complementary safety goals. For example, we require no temporary evacuation of local population. We require no long-term relocation of local population and under any accident conditions, which nobody would want to be evacuated, nobody would want to be relocated because there's a nuclear accident. So we want absolutely prevent that from happening. And these safety goals are set to complement radiological acceptance criteria. Now, those are the limits, acceptance criteria for the radiological consequences. But in reality, we often convert it to a more values that we can, the limits that we can apply to our systems. So we were developing the technical acceptance criteria for the systems based on the radiation acceptance criteria and safety goals. For example, we're developing the temperature limit, the pressure limit for the vessels, for the pipes, for the containers. Those, of course, those technical acceptance criteria will have to be discussed with and approved by the regulators. These activities are part of the pre-licensing and licensing activities. We envision that these technical acceptance criteria will include adequate safety margins, and we intend to use the technical acceptance criteria to be developed as the acceptance criteria for safety assessment. So these are the introduction of the objectives. So for any design and safety assessment, we will set this objective first. Then our design will follow those objectives. Our safety assessment will be used to demonstrate that those objectives criteria are met. Okay, so after we set the objective, we want to make sure those objectives are achieved. So we do that by going through a systematic process. So I'd like to give you a short introduction of the overview of ThorCon design and safety assessment process. So overall, the design will be divided into phases. We do that for a reason, because there's a need for a vendor to divide the design into phases to meet either regulatory requirements or business requirements. So we start with the conceptual engineering design, then followed by the preliminary engineering design, and then detail engineering. design. So at this moment, ThorCon is in the transition from the conceptual phase to the preliminary phase. So we do have a process that can give you an overview of the activities, the process. So let me actually share another document with you. Just give me a second. Okay. What I'm sharing with you at this moment is the ThorCon design process overview. So I want to walk you through the process, so you can have an understanding of how things are done within ThorCon. As you can see on the screen, if you cannot see the screen, let me know, but I'm showing you a Word document that shows the diagram of the design process. So the first step is to establish the requirements. As we just introduced, the first phase is conceptual engineering phase. So first of all, we establish the requirements. The requirements will be from the safety objectives, radiological acceptance criteria. So those are the safety requirements. And then it will also contain the business requirements. For example, how many days of a year we want to generate the power, how much power we want to generate it, what are the costs of the power. So those are all will go into the design requirements. And then we do the design, and the design then will be verified. We call it a conceptual design verification. And there's several ways of doing that. We can do design review. We can do confirmatory analysis. And most important of all, we have to do safety assessment. So, and then if the design pass the verification, we'll go into the next phase. But if it's not, if some issues are identified, we'll go back to the design requirements and review it, and we do the design update until the design passes the conceptual design verification. Then we can move on to the next phase. Now, because this diagram is just the overview, each of the step will have its own process, and we won't have the time to introduce each individual of them. I just want to give you a big picture, an overview of the whole process. So let's scroll down and move on to the next phase. So next phase is the preliminary engineering phase. In this phase, we got input from the conceptual phase because we're doing more detailed design. So we're gonna break the design into systems. So for each of the system, again, we're gonna define the preliminary system design requirements, and then we do the design. And after all the system is done, we do the preliminary design integration. After the integration, we'll do the preliminary design verification. So those are very similar to the conceptual phase, but with the difference that the system will, the design will contain several systems, because we envision that we're gonna give the work for each of the system, or you can consider that as a package to other contractors. For example, the site evaluation might be done by another company. And an important component, for example, the molten salt pump may be designed by a pump supplier. So those are ideas, but the whole design will again be verified through the review or the confirmatory analysis and safety assessment. So if we pass that, we'll move on to the next phase, which is the detailed engineering phase. So in this phase, we start with the validation. Remember, when we're in the conceptual phase, we only do the verification. And now, after the verification, we're also going to do the validation. So the difference is that the verification is done by review and analysis, assessment, but the validation is done by test. So here we have what Bob just introduced, the proficient test platform. So on that platform, we're going to do both component tests and integral tests. And we probably will have to do some other component tests separate from the PTP. When all the tests is done, we move on. When all the validation is done, we move on to the next step. So in the next step, we're gonna do the detailed design for the systems with the input from the test. And then we're gonna integrate the design into one, and we're gonna do the detailed design verification. So if we pass the verification, we'll move on to the next phase. If not, if issues are identified, we will go back to either we have to do some additional tests or we need to give some feedback to the design. So you can see it's a iterative process. So in each of the phase, we set the requirement first. We do the work, and then we do the verification. In some important stage, we also do the validation. And the results we got from the verification and validation will be feedback to the requirements, to the design itself. At the minimum, we go through this 3 times to make sure that we incorporate all the information we got from the test, from safety assessment. And if we passed all this verification and validation, we will move on. This is actually, we call it detailed design validation. It is indeed the demonstration power plant, which is ThorCon 500. And with this demonstration plant, we also do the commissioning and operation tests. So I want to convey to you the message that ThorCon's whole safety philosophy is based on tests. So not only the PTP, the proficient test is a test, it's the demonstration power plant itself will also be used as a test platform. And it's just while it's generating the power, it's also generating the information that we will need for the future generation of power plants. So once we successfully operate the ThorCon 500, we'll get new information from the power plant itself, and those information will again be fed to the design for the update of the commercial power plants. So once we got those information, we will move on to the next stage. We'll have more and more power plants. So as you can see, we continually incorporate the experience, the information we learn from operation, from a test, and we continually improve the design. So those are the overview of the ThorCon design process. I'll be happy to discuss this process with you either in this session or next week. So let's go back to the PowerPoint. Okay, so we're now back to the PowerPoint here. So in the overview of design process, we mentioned several times about safety assessment. So apparently, safety assessment is an important step for ThorCon to verify the design. And actually, it will be the main tool to verify the safety objectives, the radiological acceptance criteria are met. So it is important to understand how ThorCon is going to do with the safety assessment. So again, I'm going to introduce you to the scope of the safety assessment. I'm going to again use another document here. So let's go back to the overview of the process. Okay, so we just showed the figure 1, which is the overview of the design process. Now let me move on to the next one, next figure, which is the overview of the safety assessment. So again, as I mentioned, this is just the overview. Each of the block here represents an activity which will have its own lower level process. Some are ready, some are still under development, but this diagram gives you a big picture of the scope of safety assessment. So the safety assessment is taking information from the design. And then there's a work to be done within the safety assessment. It is a systematic approach to generate evidence that the safety objectives are met. So there's several things need to be done first. First of all, we have to identify the safety functions. We need to confirm the safety classification based on the safety functions. We need to confirm the plant states, including not only the operational states, but also the accident conditions. We need to identify the external and internal hazards. Some of the hazards can be eliminated by design, and those hazards cannot be eliminated, will go down as the postulated initial events. So once we have those information, we can start the safety analysis, which of course will start with the acceptance criteria. And those are, in many cases, are the technical acceptance criteria to be developed based on the radiological acceptance criteria. We have to take care of the uncertainty and sensitivity. Now we're using computer software. We have to do the verification and validation of the software. We have to take the operating experience into account. In the molten salt case, we have to consider both the test reactors that has been built and operate for molten salt reactor, and we also have to consider the operating experience from the LWRs because they have the most extensive experience. And within the assessment, we will do assessment on defense in depth. We will do assessment on safety functions. We will assess the radiation protection features. We will do the site assessment. We'll do the human factor assessment. Of course, our objective is to minimize the operator actions. And then we have to do the 5 protection assessment. And the 5 protection assessment will be based on the national standards that is set by the hosting countries. We also have to do the lifetime safety assessment, for example, the aging management. And potentially through the assessment, we will identify that some tests need to be done to support the assessment, which will go down as a list of tests. And then the safety assessment will generate outputs. The outputs typically would include the confirmed safety classes for items, the radiological consequence for each of the events. Some tests, additional tests may be required, and then safety limits for item important safety, design basis for item important safety, and there's other requirements. So we have listed several output, which I can show you here. So there'll be additional output from the safety assessment, such as the operating limits and conditions, requirements for operation, indication of or alarm response, anticipated operational occurrence response, inspection, maintenance, accident management, radiation protection, reliability, and etc. So let's go back to the PowerPoint. Oh, sorry. Okay. Okay. So I just did a very quick overview of the design process and safety assessment with you. I know the time is very limited. I think you might have a lot of questions, but we can try to answer that in this section and in the next week section. But the idea, the purpose I'm showing you this is to let you know that ThorCon has a systematic approach towards the design and safety assessment, and all these activities will be well controlled to make sure that we considered everything that we should consider, and so that the safety, so you have the confidence that the safety objectives are met within the design and verified by the safety assessment. Okay, so let's maybe spend some time to touch a few important topics within the safety assessment. So the safety analysis. So I want to start with the introduction of safety assessment and safety analysis. So those are the two words that are often used by experts and people. So safety assessment, according to the IEA, means a systematic a method that can demonstrate the safety objectives are met, while safety analysis usually refers to the analytical study, the numerical study of a event or topic, but it can be used interchangeably within a document. So here we're talking about safety analysis, which is really a numerical study. So safety analysis, it's usually based on studying events. So if you look at all the safety analysis report, it always study all kinds of events. So the identification of the events it's very important. And our safety analysis started with the identification of postulated initiation events. Now these PIEs are just events. It could lead to it's just the AOO, or it could lead to a DBA, or it could lead to a severe accident. So whether the PIE will lead to an accident, the safety analysis will tell us. So we started with gathering the PIEs. Now, it is kind of challenging for a new type of a power plant to have a comprehensive PIE list. So we try our best. We started with the review of Oak Ridge National Laboratory MSRE reports. So those are the only MSR has been operated in history. So they generate a lot of reports. We were able to learn their experience from those reports. And also there are studies done by academic institutes such as Argonne National Laboratory and University of California. They done studies on the PIEs for molten salt, for MSR. There's also industrial groups such as the USNS 20.2 working group. They do studies on MSR, and also they got experience on sodium cooled fast reactor, high temperature gas cooled reactor. And also there are studies based on several other sources, including the studies done by ThorCon by ourselves. So with all these sources, we have the confidence that we have considered almost all the postulated initiation events we can come up with. But even with that, we have to verify that. So what we will do is we're going to use systematic methods to verify that. For example, we can use a master logic diagram, MLD, to verify that we covered all the component failure. And we can also use hazard to identify the external and internal hazards. And those are the methods will be used to verify the PIE list. So with all these multiple sources of PIEs and with the systematic method to verify the list, we have the confidence that we will be able to identify all the important PIEs in the safety analysis. So once we identify the PIEs, we will do the categorization. So the PIEs will be categorized based on the frequency of the occurrences so that appropriate radiological acceptance criteria and analytical methodologies may be applied. So the purpose of doing the categorization is to apply the appropriate acceptance criteria and methodologies. The reason is that, for example, the PIEs that happen more frequently should have a more stringent radiological acceptance criteria. For example, if you remember, when we set up the radiological acceptance criteria, we set different dose limits for different type of events. For normal operation, we have set of limits. For AOOs, we have another limit, and for DBAs, we have another limit, which is the highest one, because the DBAs happens less frequently, while the AOOs happens more frequently. So as you can see, the categories here, for any AOOs, the frequency of occurrence should be equal to or greater than 10 to minus 2 per reactor year, while the DBAs has a less frequency of occurrence, which is between 10 to minus 2 and 10 to minus 6. And then there's any events that happen with the frequency of occurrence less than 10 to minus 6, we'll consider that a beyond design basis accident. I want to point out the design extension condition, and these are the concepts that are very popular after the happening of the Fukushima accident. So the deck is a BDBA, which has a very low frequency of occurrence, but it will be considered in the design. But when we do the analysis, we will use the best estimate methodologies for the deck. Okay, so the PIEs, the last slide showed that the PIEs will be put into different categories based on their frequency, and then the PIEs will also be grouped. So there's basically two purposes for grouping the PIEs. The first one is to improve the comprehensiveness. And the second purpose is to choose a few PIEs within each of the group to do further analysis. So realistically, it is impossible to fully analyze all the PIEs you can think of, because you can think of like several hundreds of PIEs. You won't be able to do a fully analysis for all of them. By grouping them, you can just choose some bounding PIEs and do some further analysis. So this is the reason that we do the grouping of PIEs. At this moment, the PIEs are grouped as follows. You can see there's a reactor PIEs, power conversion PIEs, safety system PIEs, external PIEs, etc. There will be subgroups. We will generate more groups so that the representative PIEs can be chosen from those groups for further analysis. So by saying so much, I want to give you our current list of PIEs, so you have a better idea what I'm talking about. So again, I need to sorry. Okay. Again, I need to switch to another document. So let me share this document. Okay. Okay, so what I'm showing to you on the screen is our current list of PIEs. As you can imagine, when the design progresses, we will likely identify additional PIEs, and we will also likely to combine several PIEs into one. So again, this is a dynamic list. The work is still ongoing. We're going to use a systematic approach to identify and to record those PIEs. So I want to start with table 1, which is a reactor PIE group. So what we did was we identify the event, then we consider how this event will progress and what mitigation actions will be taken. Then we will estimate the expected safety impact. So these are the table 1 is the reactor PIE, and then we have table 2 is the safety system PIE, and power conversion PIE, and infrastructure PIE, external hazard PIE, fuel sort and can transfer PIE. So you can see the PIE is not only for the power operation, but it also for the fuel change. It's also for the other operating mode. And then we have operate action PIE, and then we have historic PIEs. So as you can see, this is a very long list. You can imagine that we will have to choose some bounding PIEs for each of the group to do further analysis. We will also likely to generate more groups of PIE for that purpose. So I won't have time today to go into the details of the list, so I will just stop here. We'll go back to the PowerPoint slides itself. Okay. Okay, so we just talked about the PIEs here. So once we have the PIEs, we can carry on the safety analysis. Now, the safety functions are another important topic of the safety assessment. So ThorCon has the safety philosophy of 3 Cs, which are consistent with the IEA fundamental safety functions. So the IEA fundamental safety functions are control of reactivity, cooling of radioactive material, and confinement of radioactive material. So which it's corresponding to control, cool, and contain. So why we're identifying safety functions? Because we're going to use the safety functions to classify the structures, systems, and components. But the question is why we're doing this SSC classification. Because we're doing that to support the definition of the design, manufacturing, testing, and maintenance rules. Because we're going to give the SSCs with high safety importance more attention, while giving the SSCs with lower safety importance less attention, so that we can better concentrate our resources to the SSCs that has the highest safety importance. So in the ThorCon process, the SSCs are classified primarily based on the safety functions to be performed. But we're also going to consider the additional factors, such as the frequency to be called upon to perform safety functions, the consequence of failing to perform safety functions, the time to be called upon to perform safety functions following a PIE. So that means how much time we have for a safety system to start performing function after a PIE happened. So once we have the safety classes of the SSCs, we will set the rules, the design, manufacturing, testing, and maintenance rules based on the safety classes. In the ThorCon safety philosophy, we mentioned that we start with eliminating the hazards. But what if we cannot eliminate all the hazards, and then we're going to follow the defense in depth concept to address those residual hazards? So our concept is that we start with construct the plant with high quality. So our system has, with high quality, will have a less frequency to fail, will have higher reliability. But as you can imagine, the system will fail, the PIE will happen, and there's also going to be external event. And then we do that, so we control the power plant primarily by inherent and engineered features such that the actuation of safety systems are minimized by design. So we're not relying on the actuation of safety systems to maintain safety, but rather we are going to maximize the use of inherent and engineered features. But even with that, there might be, I think there will be some situations, scenarios that we have to actuate safety systems. If that happens, we do that by automatic actuation of safety systems, and rather than require the operator to take actions. So as you can see, the logic here, first of all, we have we build a systems with high quality, and then we control it by inherent and engineered features rather than actuation of safety system. If we have to actuate the system, it would be done by automatically rather than by operator actions. So those are our thinking of defense in depth. And on top of that, we also provide multiple means for ensuring that each of the fundamental safety functions performs. For example, control, we have several ways of doing the control, not only one. We have a control rod, we have a temperature reactivity feedback, and we also have a drain of the salt into the fuel drain tank, if you remember from the past week's introduction. So there's several ways of doing control. Each of them are independent of another one. And for cooling, we also have several ways of doing that. We have the cold wall, that is a passive system. And then we also have the basement water. Should the cold wall for some reason fail, the basement water will be used to cool the fuel. So there's independent ways of cooling. And there's also independent ways of contain. So as the last bullet showed here, we have 3 independent physical barriers to the release of radioactive material. So these are the ThorCon defense in depth implementation. Those are consistent with the IEA requirements. I think it's also consistent with the requirements for most of the countries. Okay, so we have just covered very briefly about the ThorCon overall design and safety assessment approach. We started with the safety philosophy. We covered the safety objectives. We covered the design of safety assessment process, and we also discussed several important topics within the safety assessment. And now I'm going to use the remaining time of this presentation to give you an introduction of some scenario we have analyzed so far. So Bob asked me to talk about a scenario that is like what happened in Fukushima Daiichi. So I will do it. I will introduce this one. So let's just review the sequence of events. So in this analysis, we try to repeat or to try to simulate what happened to the Fukushima Daiichi power plant. So we assume the ThorCon plant is in full power operation before the earthquake, and the earthquake happened at time 0, and it will be detected immediately. So that's time 0, and immediately when we detect earthquake, the system will automatically drop the control rod, and the control rod will take a few seconds to drop, but then after 45 minutes, the power plant will lose all the power sources, and not only in the grid power, but also the backup power from diesel generators, if we have any. So at 45 minutes, we lose all the power. And because we lose all the power, the pumps will all stop. And then the primary salt flow will stop. And also the secondary salt flow will stop. So once we lost the power, the power plant will automatically start to drain the fuel salt. It will take 10 minutes for the freeze valve to open, for the drain to start. So the actual drain will start at the 45 minutes plus 10 minutes. So it's about 55 minutes after the earthquake. The salt will start to drain from the port into the fusion tank. So here's on your, so let me just get the point out. Okay, so on the right, there's a picture of the reactor. Here's the core. Here's a freeze valve. So after 45 minutes of the earthquake, the freeze valve will open and the fuel salt will start to drain from both from the core and also from the heat exchanger. So you can see there's two branches here, the heat exchanger and the pot. I want to mention this because in the next few slides, when we show how the fuel salt is drained, we will discuss that the fuel salt from both heat exchanger and the pot. And I also want to remind you that there's a graphite moderator filled inside the pot, which will play an important role when we calculate the temperatures. Okay, so let's move on to the next slide to see how the, So let's review the methodologies we're using to calculate, to simulate the scenario. So we're doing the burn-up calculation with fission product removed in order to obtain the time evolution of decay heat. We're using the serpent code to do the burn-up calculation. So it's mentioned that the fission product removal, because if you remember, we have an off-gas system that's able to remove some of the fission gases during the operation. So that will be considered in the simulation. And there's a gamma transport simulation aimed at evaluating the decay heat fraction deposited in the graphite. Again, that's also been done in Serpent. And we also have a finite element calculation to fine-tune the thermal model of a graphite block, as you can see on the right. So we're using open form to do the CFD calculation. And there's also a heat transfer analysis, including radiative heat transfer for the verification and fine-tuning of the drain tank model. So let me go back to the slides. So the calculation include the heat generated and the and transfer in the pot, and then once the fuel drain into the fuel drain tank, it will also calculate the heat transfer from the fuel drain tank into the cold wall. Okay, so let's start with the fuel sort drain. So on the left is a picture. It's a curve of the fuel sort volume change over the time. On the right is the fuel sort flow rate change over the time. Now, regarding the time zero here is the starting time of the drain, which is T3. So time zero means the time you start to drain the sort, which remember is the 55 minutes after the earthquake. And here's the end of the drain. It's gonna take about 13 minutes roughly. Here's a second, so the unit is a second. So it's about 13 minutes to completely drain the fuel sort from the pot and heat exchanger to the fuel drain tank. As you can see, here's the volume change. And then on the right, is more interesting things is that the flow rate change. You see the flow rate is not changing linearly. It got some jumps here. So here's a two dashed line indicate the core boundary. So if you go back to this, the fuel sort normally would be somewhere here. The top level will be here, and then it drains through the head tanker, the pipes, the heat exchanger, and you see there's a difference in geometry, so the flow rate will change over the time. Okay, so here's the flow rate, and then let's see how the temperature would change. On the top is the outlet temperature. So we got three curves here. We have core temperature, core outlet temperature. We have heat exchanger temperature. Sorry, just okay. And then there's main temperature. So why we have these curves? And this one, the core temperature is the, if I go back to this image, sorry, I have to switch between the slides. This is the core outlet. This is the heat exchanger outlet. So when we do the drain, the source is actually coming from two different branches. Here we call it the heat exchanger branch, and this one is a core branch. You may notice that the temperature of the core branch is always lower than the heat exchanger branch. And why is that? Because there's a moderator, the bigger graphite inside the pot. It served as a, because the mass and volume, it will absorb the heat so that it keeps the fuel source in the pot lower than the fuel source in the heat exchanger. Because in the heat exchanger, you don't have any this kind of thermal inertia. So, and then the average source temperature is closer to the pot because there's just more salt from the core compared to the heat exchanger. So I want to point out that the unit of the temperature is Kelvin. So the 1000 Kelvin here is about 730 centigrade. Again, you can see the bottom one is the volume flow rate. It changes over the time because of the geometry of the system. So what does this mean? So once the fuel source is drained out from the from the can, it will enter the fuel drain tank. And these are the fuel drain tank. If you remember, those are the same cylindrical containers that the fuel source, it doesn't show the pipe, but the fuel source flow from the top and fill the fuel drain tank. And the geometry of the fuel drain tank ensure the subcriticality. So there's no chance that the fuel source will go back to critical in the fuel drain tank. The fuel drain tank is cooled by the cold wall. So it doesn't show here, but there's a cold wall outside, there's cold wall inside. What the cold wall is, it's really just the stainless container filled with water. So the heat is transferred from the fuel drain tank to the cold wall through radiation, through limited conduction and convection. And the cold wall water, because the volume of the water is huge and it circulates to the cooling pond. So the temperature of the water won't change too much. It will have enough water to cool the fuel drain tank for a long time. And here is the CFD simulation of the drain tank. So what happened to the drain tank? On the left is the drain tank temperature change over the time. Now, and here in this figure, the time zero is the ending time of the drain. So remember the last time we talked about the drain. Now the time zero is the ending time of the drain. So it's actually T3 plus 13 minutes. It's about 1 hour, 1 hour, 8 minutes after the earthquake. So start from here. And now we have about 20 hours, 1200 minutes, about 20 hours. So we simulate the time from the end of the drain all the way to 20 hours after the end of the drain. So you can see the temperature, the soil temperature and the drain tank shell temperature. Drain tank shell means the wall of the drain tank. The temperature increase in the first several hours, then it starts to go down because of the decay heat in the fuel salt increases over the time significantly, and it also the cold wall is keep cooling the drain tanks. So as you can see, the highest temperature may be somewhere over 1,000 Gray for the fuel salt, but because of the cooling of the cold wall, the drain tank wall temperature has never gone above 1,000, and it will go under 800 after 20 hours. So with this temperature, we can calculate the accumulated percentage of life depletion of the drain tank. So here's the percentage. We have both top and bottom. So why we have top and bottom? The top means the position that the fuel salt, the top level of the fuel salt, which we believe is the highest temperature point. And the bottom one is the bottom of the fuel drain tank, which we think is the point that the highest stress. So let me go back to the previous one. So if you consider this is the fuel, one of the cylinder of the fuel drain tank, if the fuel salt level is here, then this one is top, and this one is the bottom. Okay. So as you can see, the drain tank creep life depletion is always under 1%. So that means the damage that is done to the fuel drain tank is very minimal in this case. So we can have some conclusion from the preliminary analysis, and we found if a Fukushima-like scenario happens to a ThorCon power plant, the fuel salt temperature will be always under 1100 degree, which is significantly lower than the boiling point of the fuel. So the boiling point of the fuel is above 1400. So we have a big margin from the fuel temperature to the boiling point. There will be no boiling of the fuel, and there will be no increase of pressure within the system. And then the fuel drain tank temperature. Remember, the fuel drain tank is the first physical barrier to contain the radioactive material. So the first barrier, the temperature, just briefly exceed 800, but under 1,000 for the first 20 hours. And then after the first 20 hours, the temperature will go under 800. So these are the challenges to the fuel drain tank, which we consider is very minimal. And then the accumulated percentage of FDT, which is fuel drain tank creep life depletion, is less than 1%. That means theoretically, you can actually reuse the fuel drain tank. After the accident, you can pump the fuel salt back to the core, and you can continue run the power plant without having to replace the FDT. And the reactor is in a safe shutdown mode because the the fuel salt will remain subcritical due to the geometry of the fusion tank, and the temperature will be kept under safe temperature, so it can stay there for a very long time. As we introduced in the second week, the cooling of the pond and the basin water can keep the fuel salt cooled for a few hundred days. So that's a very long time. So no damage to the FDT, which is the first physical barrier to the release of radioactive material. And of course, no challenges to the second and third physical barriers. So because the first barrier only has a 1% damage, there's almost any challenges to the second and third physical barriers. And in the end, there's no release of radioactive material. So those are the results we found from analysis that simulated the Fukushima accident should it happen to the ThorCon power plants. And we were very encouraged by the findings here. Of course, this analysis has to be validated by tests. So that's why we're going to have this precision test platform, the PTP, and on that PTP, we can do actual tests to validate this analysis. Okay, so we have spent some time on the Fukushima-like scenario. Our analysis did not stop there. We also analyzed several other MSR events. So those events are very typical to MSR, which has been studied by others, by either Oak Ridge National Laboratory or some other academic institutes. So those 3 events we select were loss of flow, which means we don't have any flow in our loop. We have loss of heat sink. So normally our heat sink is it's through the steam cycle, then it to the seawater. So we assume for some reason we lose that heat sink. The third one is inadvertently open of freeze valve. Remember, we have 4 freeze valves that's underneath the can connected to the filtering tank. Now, the purpose that we have 4 valves in parallel is to ensure that the freeze valve will open when we have an accident like Fukushima. But there's also a possibility that the freeze valve will open inadvertently by itself. So we also analyze what's going to happen if the freeze valve opened by itself. So by going through the analysis of all these 3 events, we actually reached the same conclusion as the Fukushima-like scenario. The reactor will always go into the safe shutdown mode. There was no damage to the FDT, the first physical barrier. There was no challenges to the second and third physical barriers. No release of radioactive material, which is not a surprise at all, because the design of the ThorCon power plant, which is based on molten salt technology, and has the advantage of managing or survive the events we just mentioned. And these events are very serious for a technology like high pressure light water technology, but due to the inherent safety features and the special design of the ThorCon power plants, it's relatively comfortable to manage these events. Again, I want to emphasize that these are just preliminary design assist analysis. We will do further analysis to get more information, and we also going to do a test to validate the conclusion of those analysis. Again, ThorCon's philosophy is to demonstrate the safety by test. Okay, that concludes my presentation for this week. We do have several references here. If you're interested, we can provide those references if it's allowed by export control and other restrictions. But I do enjoy the opportunity that to present this result to you. I'm looking forward for the discussion with you. Thank you very much.
Thank you very much, Kun. So before we go to the question and answer, as usual, let's take a picture of the whole group together. So if you can please close down the screen sharing.
Yeah, let me stop it. Okay.
Okay, so please everybody show up your video. Yuri, are you ready, Yuri? Make account.
Ya, Pak. Okay, the first slide first. 1, 2, 3, smile. Second slide. Please open up your camera, everyone. Okay, the second slide. 1, 2, 3, smile. Last one. 1, 2, 3, smile. Okay, Pak Bob.
Okay, thank you very much, Yuri. So question and answer. We have several questions here already. I see Lars is joining with us. So, okay, the first question is from Endia Puji. So she asks, in the SMR safety analysis, do you apply DBA or up to BDBA? What is the worst accident scenario assumed in the SMR safety design? So there's two questions there.
Yes.
Okay, please.
Okay, thank you very much for the question. For the first one, the simple answer is both. The difference between DBA and the BDBA is that the DBA will be analyzed using conservative methods, while the BDBA will be analyzed using a best estimate method. The DBA will be the analysis of the DBA will be used in the design, so that design will be able to defend against a DBA. Now, the IEA safety standards do not require a power plant to be designed against the BDBA, but it does require that the design extension conditions be considered by the power plant design. So when we say we will analyze BDBA, we're actually saying we will analyze the design extension conditions. So the second question is, what is the worst accident?
Yes.
Sorry, Bob. What's your?
Yeah. What is the worst accident scenario assumed in the SMR safety design? The worst scenario.
Okay, this is a very interesting question. So my personal belief is that we have to go through the systematic safety assessment to really identify the worst accident scenario. There of course there's some thinking that one or two accident can be the worst one, but I'm hesitant to tell you at this time that which one is the worst one. But I will ensure you that all the important accidents will be analyzed, and we eventually will know that from the safety assessment.
Okay, so the next one from Dr. Petit. Don't you need to screen these PIE based on the probability or probability estimate given there is no operating ThorCon reactor, maybe based on the experience from similar reactor? In other words, these PIE do not have same probability of occurrence. Interesting questions.
Yes. So let me just make 2 points here. First of all, these PIE, we will consider the frequency of occurrence of these PIEs. Of course, some of them will be AOOs, some of them will be DBAs, some of them will be BDBAs. So we have to consider their frequency of occurrence so that more resources can be given to the event that's going to happen more frequently. So that's the basic principle. And then the second point is about the PSA. So once you, let's say once you have the frequencies, can you do a PSA for a new power plant like ThorCon 500? And my thinking is that there hasn't been any industrial consensus on this PSA on how to do the PSA on molten salt reactors. So I would prefer to discuss this with the industry to reach a consensus. Then we can start with that. But before we can reach a consensus, I would not jump into the PSA at this moment.
Okay, Pak Petit, is that satisfy you, or do you have follow-up issue on these questions? Pak Petit?
Yeah, thank you so much. I understand that this is like really early phase that we're not able to evaluate all PIEs, postulated initiating events, and there are simply too numerous of them. And I think later during design review, then we have a more thorough and deeper look into this. And as you said, Dr. Kun, that then we will have to develop a framework for PSA and whether or not this is in line with the current industrial practice. But basically, yeah, so I understand the limitation here, but this is something that we need to discuss in the future. Thank you.
All right, thank you very much. I think that was satisfying. So the next one was from Ibu Endia again. In SSC classification, apart from safety classification, what other factor need to be considered? Has the quality class has been considered attached to the safety class so that it does not need to be classified based on the quality class? Considering that Indonesia is an earthquake zone, is the classification based on seismicity not taken into account? So
yeah,
you
okay.
understand? Do you understand, Kun?
Yeah.
Questions? Okay,
yes,
good.
Yes. So this is a very good question. We do the classification of SSCs. First of all, we do the safety classification. Then based on the safety classification, we can consider the quality, the seismic, and also the mechanical components, the structures, the I&C systems. So it's all related to safety classification, because we want to make sure that the SSCs that has the highest safety importance will be designed and manufactured, tested, and operated using the appropriate engineering rules. In terms of the quality, when we consider the quality requirements, it will not only consider the safety importance, but it also will consider the level of maturity of the technology, which is very common practice. When you consider the seismic classes, it will not only consider the safety, but also, as you mentioned in the question, it will also consider the local situation. So I guess to summarize my answers, safety importance, safety is a very important factor, but other factors will also be considered. And for each of the quality, seismic, different factors will absolutely be considered.
So is that satisfying, Bu Endia? Any follow-up on the question, Bu Endia?
Thank you. It is enough.
Okay, very good. Thank you very much, Bu Endia. Next one from Febri. There's 3-part questions, Kun. One is, when the plan will be commercialization from the demonstration plan? You said that there will be some updates in the detailed design. Will you provide me the example for those updates? 2, in the determining safety classification, does it have same method and criteria as all WR? 3, in the safety analysis for the MSR design, do you implement the practical elimination concept? Okay, do you understand the questions?
Yes, yes.
Okay.
So for the first question, I hope I can give you a very detailed answer, but unfortunately, it's too far. I mean, that at least several years from now, but I can imagine some of the improvement we could potentially make when we complete the demonstration plan. For example, the operating procedure of the power plant can definitely be improved once we have the experience of the demonstration plan. For example, how are we gonna remove the can? How are we gonna replace the can? How are we gonna change the fuel? Those type of things can definitely benefit from operating the demonstration plant. For the second question, I don't think the method will be the same as LWRs. So the requirements will be similar, but the method will not be the same, because the LWR has far more systems, far more SSCs compared to the ThorCon 500, and also the how the system work will also be different from LWR. So we are developing the method to classify the ThorCon 500 SSCs based on safety, but I can tell you at this moment it won't be the same as the LWRs, but it will ensure that the high-level requirements are met. Third question, in safety analysis for MSR design, do you implement the practical elimination concept? Well, the practical elimination concept is based on the frequency of occurrence. So when the frequency is extremely low, you would say it's practically eliminated. Which again, going back to the previous question regarding PSA, it is a challenge for any new concepts. It is very challenging to calculate the frequency accurately. Actually, I think even for the LWRs, it's, I mean, the actual quantitative value is still arguable, right? I mean, you have this a situation that you say this, let's say this storm, this earthquake, this heavy rain is going to be over 1,000 years, but then you say it happens almost every other year. So then people start to question if the frequency you calculated is accurate or not. So with all these challenges, the ThorCon approach is that actually from the determinist point that we want to make sure that multiple barriers exist, so that this the happening of the consequence, the happening of the release of radioactive material will be almost impossible. But again, I'm open to the discussion of the concept of a practical elimination. I think that's a good point that we as a applicant can discuss with the regulators in the licensing process.
Okay,
I'd
very
like
good.
to, Bob, I'd
Yes,
like to put in
please,
a little
please.
bit on this.
Please, Lars.
So in terms of practical elimination, if you look at history, human error has been involved in all three of the accidents that we've had. 3 Mile Island, a maintenance worker put a valve in the wrong position. At Chernobyl, well, there was a slew of human errors. And then at Fukushima, they didn't relieve the pressure at the time that was called for. They held off, and as a result, they ended up with the explosion. So we have practically eliminated human error in that humans are not involved in the safety system. So there's no action the humans have to take to activate any safety systems. There's no actions they need to take during the protection against an event, and there's no action that they can take to prevent the safety system from shutting the system down if anything goes wrong. So that's the first real elimination of the primary, of one of the largest causes of accidents. The second one was the loss of electricity, full station blackout. That really caused a lot of problems at Fukushima. It is becoming the norm that new plants have to handle that. And when you do that, you've eliminated loss of electricity as a cause of accidents, because we've made it so that if we lose electricity, we safely shut down. We are fortunate in that, different than an airplane, when an airplane has trouble, they have to manage and fly and get to the ground. So they have to be actively doing stuff. In our case, if we get in any kind of trouble, we drain and it's cooled, it's done. It can go to safe shutdown conditions purely by gravity. Thanks.
So, okay. So I guess Bu Febri, is that answer your question, Bu Febri?
Yes.
Pak Febri, Pak Febri. Pak Febri, Pak. Mas Febri.
Okay. Oh,
Okay.
sorry, Pak Febri. Pak Febri. Oh, Mas Febri. Sorry. Salam kenal, Pak Febri. Okay, very good. Jadi it's that answer, or do you have follow-up question, Pak Febri? Okay,
No,
I guess not.
That's fine.
Okay. Okay. All right. So the next one from Dr. Aziz about the prevision. As the prevision test platform is subcritical, how do you simulate the reactor behavior under reactivity change, such as reactivity insertion accident? Do you conduct probability safety assessment as the risk is defined through deterministic assessment, and PSA, how you define the risk. 3, in doing DBA analysis, do you apply single failure criteria, which assume the first safety system failed to perform its function, and instead the second one eventually takes safety? 4, what is the most limiting PIEs in each group? That's a lot of questions there. Kun,
Yeah.
do you? Okay.
Yeah. Yeah, absolutely. Those are very excellent questions. Let me start with the first one. Yes, you're right. The PTP, it does not have any nuclear fuel. The limitation is that we won't be able to measure neutronics parameters like temperature, reactivity, feedback coefficient. We won't be able to do that. But we can simulate some of the reactivity in certain accidents. We can make assumption, we can using calculation to predict the heat generated in the reactivity insertion. We can simulate the thermohydraulics part of that accident. But the neutrons part won't be able to done. We won't be able to do it on the PTP. It has to be done on the demonstration plant or some other critical setup. The second question is the PSA. So again, our position is without the industrial consensus on how to conduct PSA on a molten salt reactor, we won't jump into that. Instead, we're gonna primarily rely on the deterministic safe analysis supplemented by some methods we can borrow from the PSA. How do we define the risk? So if we do the DSA, the deterministic safe analysis, we're gonna be based our analysis on the DBAs. So the identification of the DBAs is very important for us. The third question, in doing DBA analysis, do you apply single failure criteria? Yes, absolutely. We will follow the requirements of a typical DBA analysis. So yes, every criteria will be followed. The last question, what are the most limiting PIEs in each group? We're still doing the work to group the PIEs. As you can see, we only have 8 groups. We intend to have more of that. After that, we're gonna identify the most limiting PIEs for each of the groups. So I guess the answer is the work is ongoing. Okay.
Okay, thank you very much. So while we are talking about, are you there with us, Lars? Lars? So maybe Lars can add several things on the prevision. Lars? Also, I guess not. So maybe I'll ask this to you, Kun. So what actually are going to be tested in the prevision test platform? What sort of tests could you elaborate to the audience here? And what cannot be tested in the prevision test platform? So could you elaborate on this issue?
Okay, there's actually several important groups of tests we can do on the PTP. The first one is thermohydraulics. We're going to use electric heaters. So the heat transfer and fluid dynamics can be tested on that platform. And what we want to do is we want to do a full scale test. So the scale is 1-to-1. So that will avoid the scaling analysis to some point. And so that's the first group of tests. The second one is the operation. So it is very important for us to understand how a molten salt power plant should be operated, which is not a trivial thing. As you can imagine, there's only one, the Oak Ridge National Laboratory MSRE has been operated for 4 years, but that was a very small one. So we want to gain this experience from the PTP, so that when we build the demonstration reactor, we can have that knowledge, so we can make sure that the SSCs are designed in such a way that it will make the operation, maintenance, and testing much easier. So that's going to be a tremendous knowledge from the PTP. And the second one the third group of tests I want to point out is the test of the individual component. So imagine this, if we don't have the PTP, then the manufacturer, the supplier, will just make the components directly for the demonstration power plant. They will not have experience. And they probably gonna meet some challenges when they try to develop those components. But when we have the PTP, and they have a chance to practice that. So once we done the PTP, the suppliers, the manufacturer will be ready for the demonstration plant. So it will minimize the possibility of delay of the demonstration plant. As you can see, around the world, a lot of a nuclear power plant was delayed because some of the components were not developed and tested on time. And by having this PTP, we hope we can minimize and even eliminate those type of situations. What cannot be tested? Of course, the neutronics cannot be tested. So the neutronics can either be tested on the demonstration plant through let's say a phased commissioning, or it can be tested somewhere else. So those are the benefits and the limitation of the PTP. I can see Lars is back, so maybe Lars, you have some.
Yes, Lars, you have a thought to share what kind of tests that's going to be done in the PTP, since most of them are BEP10, so maybe that's what they're thinking. What are the tests regime that you're gonna do in the PTP? Yeah.
So first off, it's just basic engineering, making sure all the parts fit together. Then running the pumps at full speed and checking that vibrations in the pipes from the hydraulics and stuff are good. Then we can do temperature tests. We are limited by the 10 megawatts heat, but we can run the salt at a low flow and put in a small, 1% sized heat exchanger, so that the delta T and the flow through the heat exchanger is correct, the flow velocity through the heat exchanger, and check for vibrations in the heat exchanger and pressure losses in the heat exchanger. Then we can heat the salt to higher temperatures and do a drain. And in the drain tank, run a heater that mimics the decay heat and verify the decay heat gets removed from the drain tanks to the cold wall to the pond as we expect. Then we can test by heating the salt to a very high temperature and draining it to be sure that the drain tank can take the very high temperature. We may end up having to do that on more of a component test than a full system test, just because getting the salt up to that high temperature and holding it there might be difficult, more power than we can arrange for. We can measure the time that the shutdown rods take to drop. We can measure the coast down time and the ramp up time for the pumps. We can measure the drain times, make sure all that correlates with what the software simulation said. Those are the ones that come to mind off the top of my head. But we
All right.
Okay.
Yes, please continue, Lars.
We would also look to see what tests Oak Ridge did in the MSRE before they started with nuclear tests, and be sure we cover the same basis. And how long it takes to open the freeze valve, and how long it takes to close it, and how long it takes to transfer fuel from the drain tank up to the main tank. What's the maximum addition rate we can get from the makeup tank? These will all feed into maximum reactivity insertion rates. So we can measure all those things before we get to the demonstration plant. Okay.
All right.
That's all I have.
Thank you very much. Right. Thank you very much. That's so a lot of testing in the PTP. So moving on, we got Muhammad. So TMSR 500 has two design, which is land-based and floating NPP. I think, is there any significant difference in TMSR key SSC between the land-based and the floating NPP? I guess there's miscommunication here. In the PI categorization, is there category regarding failure in off-gas systems?
Okay, Bob, let me try to answer this question. So the presentation I've been given for the past several weeks were based on what's so-called the land-based design of the power plant. Sometimes in some documents we call it ThorCon IO. There's some differences there between the floating one and the land-based one. For example, one of the differences is how you hand the cans and other components in the power plant. But I don't think I've mentioned that in the presentation. We were just focusing on the land-based version.
Can I interrupt there for a second?
Yeah.
In the early days, we had a completely land-based version that would be assembled on land at the power plant site. That would be applicable to places like India, where you have some large rivers, but interior, pretty far from the coast. For Indonesia, we have focused on the ThorCon Isle, which is built in as a ship. We are not pursuing the land-based one at the moment. We'll chase that a little later. The reasoning is Indonesia is really an ocean-based world, and power plants that are located close to the ocean would be quite sufficient for Indonesia. And we have much better control over the risks involved, especially the schedule risks, when it's a ship-based one, because that's completely built at the shipyard. So we have a finished power plant on a firm fixed price, fixed schedule contract basis. If we do actually construct one on land, bringing the pieces in, then you end up using local labor, and the schedule is much harder to hold. And we think as a corporation, it's very important for us to hit our cost and schedule for the first plants. Nuclear has a bad reputation for not being able to do that. As far as significant differences, the biggest difference is going to be on how it handles earthquakes, but also the idea that we constructed in a shipyard versus constructing it on land will introduce some differences. We do try to keep them as close as we can, but there are some concepts that we have had with the ThorCon Isle that are not as available for the land-based one. Okay.
I don't know if Mohammed means floating MPP. Can you maybe
So
clarify on what?
Yeah, our NPP is not actually floating. It is in the ocean, but it's not floating. It's ballasted down to the seabed. So it should fall under land-based rules because it is sitting on the land, but it is not deep inland. So if you see some things from our website, you'll see a land-based deployment that's intended to be upriver and assembled at a site, rather than being able to use the ocean where we have a very large freeway that we can bring in a finished plant. Completely floating NPP is something that we have not seriously considered. There are extra challenges with the completely floating NPP. It does eliminate the problems with earthquakes and tsunamis if you're floating in deep water, but it introduces the challenge of how do you deal with a terrorist attack, not by a plane, but rather by a big ship. And I personally don't see a good way to deal with that. So we have not dealt with a pure floating NPP.
All right.
So I get, sorry, Bob, I guess
Yeah.
I can summarize this. It's like so for the past several weeks, what we introduced is not a floating MPP. It's rather an MPP manufactured in a shipyard, and then it's towed to the site and put on the a seabed, rather like a land-based foundation.
Right. Okay. Okay. Right. I think that answer categorization is there by category for failure in the off-gas system.
Okay, that's a good question. Sharp eyes. There are PIEs regarding the failure of the off-gas system. We currently put them into the category 1, which is the reactor PIE. Sorry, not category, but groups. But as I said, in the future, we want to divide the large group maybe into smaller ones, so that it's possible that we can have a separate PIE group just for the off-gas system.
Okay, so Lars, you want to add something on the off-gas, PIE off-gas system? No? All right, so going on to the next one, Zulfiandri, how long will you obtain data to prove ThorCon technology is safe from the verification and validation design, as you said in the flowcharts? How long do you obtain data? Okay.
Okay. Yeah, that's a question I guess Lars can have some answers.
Lars,
but let me start with.
Yeah. Sure.
Let me start with this. But yeah, sorry.
The plan is that we will be testing the pre-fission plant for a full year of testing before we start building the demonstration plant. We'll continue testing the pre-fission plant during the build of the demonstration plant, so that'll give it a second year. Then we will move to testing on the demonstration plant, which, as I recall, has 2 years of testing involved in it. And at that point, we would like to get a preliminary commercial license to start building more, but the endurance testing will continue to go on. And even once we finish the endurance testing on the demonstration plant, we will use that plant to test any upgrades to components Any changes to the plants will test first at the demonstration plant. So all total on the order of 6 years to get from where we are now to where we're ready to get a commercial license. Does that answer your question?
So Kun, do you want to add?
Yeah, I just want to add one point here that
so,
when we talked about the tests, the tests are considered to be validation, while the confirmatory analysis, safety assessment, design review, those are all considered as verification. So that's the only point I want to add.
So Lars, by the second year testing of the PTP, can be that considered a validation of the design?
Yes, for the functions of cool and contain.
Cool and
So
contain.
we'll be able to validate that we remove the decay heat because we can mimic the decay heat with electricity. We'll be able to validate that we can keep everything contained. We can pressurize the various containments and show that they hold the radioactive products in place. We will not be able to verify the control side of the safety functions using the PTP. That has to come in the demonstration plant, which we will do first by going step by step. So we'll start out redoing the non-fissile tests, and then we'll step to subcritical, verify that they match with the software simulations. Then we'll go to modest power, maybe 1 megawatt, and verify that things are behaving as we expect there, and that the drain works the way we expect, and step on up until we're up to full power, repeating a bunch of tests at each power level to show that it is safe, it's following the predictions of software, and getting approval to go to the next power level as we step by step commission it.
All right, very good. So I guess that was the last question. So anybody else questions before we resume, before you close down the sessions? Nobody else? Just show. Okay, I guess that's it. So Pak Tagor, please give us a resume.
Thank you, Pak Bob. Yeah, just based on the presentation from Dr. Kun and some explanation also from Mr. Lars, I think we have some points related to the weeks number 6. I think the ThorCon philosophy are 3 C's: control, cool, contain, and also the philosophy including the eliminate hazard by design, defense in depth, safety by test, demonstrate the requirements by some tests. The safety objectives, goals, and as well as radiological, technical acceptance criteria based on the IA safety standards are applicated in the design of ThorCon 500, such as less than 0.5 millisievert for any anticipated operational occurrence, and also less than 20 millisievert for any design basis accident DBA. I think the number 4, the point number 4 is preliminary engineering design of ThorCon has been done. Over the overview safety assessment process that used in the design process of ThorCon has been presented. The PIEs are gathered from multiple sources sources in the conceptual design phase. VIs are categorized based on the frequency occurrence so that appropriate radiological acceptance criteria and analytical methodologies may be applied or graded approach. PIs are grouped to improve the comprehensiveness and to choose representing PIs of the groups for further analysis. The PIs of ThorCon 500 are grouped based on their origin. Defense in the concept is implemented in the ThorCon 500. The analysis scenario like Fukushima Daiichi for the ThorCon 500.
Tycho,
Yeah.
Sorry for the interruption.
Yeah.
Can you go back to the previous slide?
Yes, Kun, please.
I don't think item 4 is correct.
Okay.
We didn't mention that. You probably want to just remove this item 4.
Okay, wait a moment.
Thank you.
Yes, good. Okay, wait a moment. And I think we go started. Okay, some important conclusions are given. I mean, for the scenario like Fukushima Daiichi, such as fuel salt temperature under 1100 centigrade, significantly lower than the boiling point, and FDT temperatures briefly exceed 800 C, but under 1000 C for the first 24 hours, then under 800 C after 24 hours. I think that's all the points from the presentation from Dr. Kun that I can make in this moment. Thank you very much.
Thank you very much, Pa Tagor. So, Kun, last words before we close this session, and this would be the last presentation session. Remember, guys, next week is the question and answer only. So everybody prepare your answer for next week. There'll be Professor Kun, Lars, and of course, I think Manu will be there. So Kun, last words before we close.
Well, thank you all very much for participating in this week's workshop. As Bob said, it's the last presentation. Next week, we're going to enter into the Q&A session. I hope we will be able to answer your questions. And Bob and Tycho, if we could get the questions in advance, we'll be able to prepare for them better.
Yes. All right. So Lars, are you still here? You want to say something?
I'm still here.
Yeah. Well, last word, last. This is the last week.
Well, I'd like to thank Kun for doing a very good job, and all the folks hanging on for late into the evening for you. Hopefully, it's been productive for you. Thank you.
All right. Very good. Thank you very much. Remember, guys, next week, prepare the question ahead of time. We hope people can give us question in the WhatsApp group to Patagor. So Lars and Kun and maybe Manu can prepare the answer, maybe with some example, maybe with some presentation to answer all of your questions. Thank you very much, guys. Good night, good evening. Assalamualaikum warahmatullahi wabarakatuh. Bye-bye now.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah. Thank you. Bye-bye.
Bye-bye.
Yeah.
Oke, thank you. Terima kasih, Pak.
Terima kasih.
Terima kasih, Pak.
Bye.